Hello, my name is Felicity McCormack and I'm an ice sheet modeller with the Antarctic Gateway Partnership at the Institute for Marine and Antarctic Studies, although currently based out of sunny Cullen, California at the University of California in Irvine, where I'm a Fulbright postdoctoral scholar for the year. I'm going to talk to you about one of my favourite subjects. So I volunteered at the biennial Australian Antarctic Festival week in Hobart in 2018. With other staff from UTAS, my role was to describe some of the research that we do into the physical Antarctic environment. One thing that constantly amazes people when I describe what I do is that the Antarctic ice sheet, so the ice in Antarctica that rests on grounded Earth, is constantly moving. It flows under the weight of gravity, which pushes ice from the centre of Antarctica towards the coast. We had this figure of the surface speed on a poster at the stand, and we asked the students to describe the figure. What does it tell us? One of my favourite memories of the day was the response to that question by a particular group of students who described the flow of ice like a complex web of rivers, or the branches of a gigantic tree winding and moving as if blown by the wind. This was a new perspective for me, and it highlighted the fact that this continent is alive and moving, dynamic and changing, albeit on longer timescales than a flowing river or a bending tree. But why do we care that Antarctica is moving, apart from the fact that it's just really interesting? Antarctica is part of a global hydrological cycle that marries ocean, ice, and atmosphere. As Antarctic ice flows to the coast, it comes into contact with the ocean, sending out floating ice shelves that are still connected to the massive grounded ice sheet. When ice goes from resting on grounded ice, Earth, to floating on the ocean, it can raise the global sea level, just like if you add a cube of ice to your glass of water. But that's only half the story. Ocean water evaporates into the atmosphere and is transported back to Antarctica where it falls as snow. In this way, there can be a delicate balance between the mass of ice that Antarctica contributes to global sea levels and the mass of ice that's returned to Antarctica through ocean and atmosphere evolution. But we're not in a state of balance at the moment. Antarctica contains enough ice that if it were all to melt, the global sea levels would rise by about 63 metres. Now, this is not going to happen in any of our lifetimes, perhaps never, but Antarctica is currently losing the equivalent of 3 Olympic-sized swimming pools every second. That's 43.5 million Olympic-sized swimming pools every year, about 109 gigatons per year. This is happening because Antarctica is very sensitive to its surrounds, oceans, atmospheres, solid Earth. The balance of Antarctic ice mass is delicate, but as the oceans are warming, the floating ice shelves are melting, and shedding of icebergs is increasing. As this ice is removed from the margins of Antarctica, the inland ice is thinning and accelerating, so that more ice is making its way into the oceans. Antarctica's ice mass loss to the ocean has been increasing over time, and if we continue to emit greenhouse gases at the current rate, we could see between 40 and 45 centimetres of sea level rise from Antarctica alone to the end of the 21st century. And that's in addition to about 90 centimetres from other sources. But there's a lot of uncertainty around these numbers. You can imagine, with its harsh environment, that it's incredibly difficult to make observations of Antarctica. And our historical record is relatively short, especially compared with other regions of the globe that are more inviting and accessible. We want to know how the balance of ice mass in Antarctica will play out into the future. How much sea level rise will we expect from Antarctica and by when? To answer this, we turn to ice sheet models. My research uses ice sheet models. Models is a fancy term really to describe the conglomeration of mathematical equations and real-world data that collectively use to shed light on the past, the present, and the future of complex physical phenomena. The model works by partitioning the ice sheet into blocks or grids. Each grid cell carries information on the observations, maybe ice thickness, speed, or temperature, relating unique bits of information between neighbouring cells. The model then solves mathematical equations at the grid level on how the physical properties of ice might change over time, which are summed to give us information on the global ice sheet level. I use models to simulate how ice in Antarctica moves, past, present and future. We tend to think of Antarctica as one giant block of ice, but actually this mass is made up of microscopic ice crystals, bonds of hydrogen and oxygen atoms. And it turns out that one of the main ways that Antarctic ice flows is by the movement of crystals within and between one another. This movement is affectionately called the creep of ice. Ice creep says that the movement of ice that's kilometres thick in some places depends in part on the movement of ice crystals that are nanometers thick. These crystalline movements are occurring continuously, second by second, feeding into flow rates of ice that range from metres to kilometres per year, and with large-scale changes occurring over millennia to billions of years. The other major way that ice moves is by sliding. At the base of the ice sheet, where the ice comes into contact with the bedrock below, there's a subglacial hydrological system, a series of lakes, channels, rivers, and sheets of liquid water. This water is produced because the rocks at the base of the ice sheet can be hotter than the ice, also because ice moves over rocks, generating frictional heat, and finally because creeping ice releases energy. All of these processes cause melt. And in the presence of water, ice can move faster because it's less constrained by the frictional forces generated where ice and bedrock meet. Because of sliding, we can see a vast variation in the speed of ice. In the interior of Antarctica, where the ice is cold and mainly frozen to bedrock, creeping is the dominant mechanism of ice movement, and the flow of ice is generally slow, maybe less than 50 metres per year. However, as the ice moves to the coasts, more basal water is generated so that the ice accelerates, reaching speeds of multiple kilometres per year, and herein lies a big challenge, reaching across all the scales, space and time, of ice flow to understand how Antarctica is changing. I'm interested in how ice sheet models reach across scales to simulate how ice in Antarctica moves, so that we can estimate how it will contribute to sea level rise in the future. A big challenge in our ice sheet modelling research is in finding a way to reach across these broad temporal and spatial scales that are so fundamental to how the complex Antarctic system operates. We can do this by downscaling, perhaps focusing on one or two regions of Antarctica in detail, then summing them up to build a bigger picture of how Antarctic ice flows. We can do this by making mathematical approximations that allow us to estimate how fine-scale processes will impact on larger spatial scales and longer time scales. As I'm speaking, I'm imagining a piece of tapestry. Though you can't necessarily see the individual threads, they are each integral to making up the big picture. The large-scale masterpiece is not complete without the small details. So it is with my research modelling the flow of ice in Antarctica and its reach from the fine scale to the large scale. And perhaps so it is in the way that we can understand, interact with and make sense of Antarctica through this collaboration and through First Light. The picture is enriched by multiple unique perspectives that cross over music, humanities, cultural studies and sciences. I'm excited to see how this tapestry is constructed, as much as the final product. Thank you.